Let's continue our adventure through geometric algebra by returning to the basics, by talking about some high school trigonometry. Here's what we're going to accomplish in this video. We're going to first review GR2. This is the geometric algebra of R2, of two-dimensional space. Then we're going to review the geometric product, the dot product, and the wedge product. Then finally, we're going to derive some familiar trig theorems. First, the law of sines, and then we're going to wrap it up with the law of cosines. So recall that within the geometric algebra of R2, we had really three different types of objects. First, we had the vectors, or the grade ones. We had two basis vectors there. We started with E1 and E2. Here's E1 and here's E2. Then we started talking about the dot product, so we had to throw in some scalars, or the grade zero objects. These were visualized by points, having a magnitude with no direction. And then the third type of object was the bivector, which is constructed by taking the wedge product between E1 and E2, and we would get objects that look something like E1 times E2, or some scalar times that. And remember, these were visualized by constructing a parallelogram using E1, in this case E1 and E2, as the sides, and including an orientation. In this case, I have E1 wedge E2, or just E1 E2, and I designate the orientation with a counterclockwise symbol. So if this is all foreign to you, please check out the first two videos where I go through all this in more detail. After we constructed the objects, or during the construction of the objects, we talked about the geometric product. So if I have two vectors, u and v, the geometric product uv is the sum of the dot product, u dot v, with the wedge product, u wedge v. And from this, we saw that if we square a vector under the geometric product, we get a pure scalar, and that scalar is the squared magnitude of the vector. So that's one important thing to keep in mind. We also found that instead of writing the geometric product in terms of the dot product and wedge product, that we can do the converse. We can write the dot product and the wedge product in terms of the geometric product. And this is what we accomplished last video. We found that u dot v is equal to 1/2 uv plus vu. And then we also found that u wedge v is equal to 1/2 uv minus vu. Let me also remind you of a formula that you may have already seen for the dot product. So if we had two vectors, let's say u and v, we want to take the dot product between them. The formula for doing that is the magnitude of u, or the length of u, times the magnitude of v, times the cosine of the angle in between them. So pictorially, if we have u, and we have another vector v, these vectors have some angle in between them. The dot product is going to be given by that formula. As you can see on the right-hand side, we have a pure scalar. There's actually another way of writing the wedge product that we haven't yet talked about. So let's say I had two vectors, let's say u and v. I take the wedge product between them. And remember what this is pictorially. I have some vector u. Let's say I have another one v. I construct a parallelogram using those two vectors as the sides. I'm taking u wedge v, so I put the counterclockwise orientation. And these vectors are going to have some angle in between them. Let's call it theta. So what I get out of this computation is going to be a bivector. It's going to be some scalar multiple of the basis bivector, which remember was E1 times E2. Now the question is, what scalar multiple is it? Remember, the magnitude of this bivector is going to be taken to be the area of the parallelogram formed here. So how do I calculate the area of a parallelogram? I multiply the base times the height. So what's the base of this parallelogram? It's just the length of this vector here. So let me write that. Length of u, or magnitude of u. Then I need to multiply that by the height of the parallelogram. And I can calculate the height by forming this right triangle here, where the length of v serves as the hypotenuse, and this opposite side, with respect to this angle, is going to have a length of v times the sine of theta. Sine because it's opposite. So that's actually another way of writing the wedge product. It's going to be this scalar multiple, which is length of u times length of v times sine theta, times the basis bivector E1, E2. And notice this is quite similar to the cross product, where instead of E1, E2, you would have some unit normal given by the right-hand rule, but the scalar multiple out in front is going to have something to do with the area of the parallelogram formed by u and v. So quite similar to the cross product. Once you recall these two formulas for the dot product and the wedge product, there's actually a neat way to write the geometric product, which I'll say for you as an exercise. To set up the exercise, remember that E1, E2 was also given the name I. Now, why did we call I? Because E1, E2 squares to minus 1. and we showed that in our first video. So what I'd like you to show is that the geometric product, uv, can also be written in the form the magnitude of u times the magnitude of v times e. Now this is the Euler constant, e to the power of theta times I. So this is a kind of neat way to write the geometric product that combines dot product and wedge product. So not relevant to this video, so I don't want to spend too much time on it, but show this as an exercise. So with the review taken care of, let's actually do some trigonometry. And let me show you how we can use some geometric algebra concepts to get another look at the law of sines. So to start, I'm going to construct a triangle. Let's say I have some vector, which I'll call B. And then I have another vector, which I'll call C. And then what I'm going to do is I'm going to add these two vectors to form a third vector called A, which forms this triangle here. So those are the three sides of the triangle. Then I'm going to stick some angles on here. I'm going to stick the angle opposite A. I'm going to call that alpha. The one opposite B, which is up there, I'm going to call beta. And the one opposite C, I'm going to call gamma. So the way that I've constructed it allows me to say that A is the vector sum of B and C. So let's start playing around with some geometric algebra concepts. What I'm going to do is I'm going to consider the wedge product B wedge A. So what I'm going to do now is I'm going to use this equation to rewrite B as A minus C. Just doing a little rearranging. Now I'm going to substitute that B right into that first vector in the wedge product. So B wedge A is equal to A minus C wedged with A. And now what I'm going to do is I'm going to distribute the wedge product to both of these terms here. So first I have A wedge A. And secondly I have minus C wedge A. What's A wedge A? Well, it's any vector wedged with itself that goes to 0. So I'm left with minus C wedge A. But remember, I can flip the order of the two vectors as long as I include a minus sign. So minus C wedge A is actually equal to minus minus A wedge C, or just plain old A wedge C. So what I've discovered here is that B wedge A is the same bivector as A wedge C. So this is actually a pretty interesting statement already, that B wedge A has to be the same thing as A wedge C. And I've attempted to illustrate that up here. So what this equation implies is that if I construct a parallelogram using B and A as the sides, that parallelogram has to have the same area as a parallelogram constructed using A and C as the two sides. So the parallelogram constructed using B and A as sides is going to be this parallelogram here. And if you construct the one using A and C as sides, that's going to be this parallelogram here. And what this equation is saying is that those two parallelograms have to have the same area. But to derive the law of sines, we're going to go a little bit further than this equation and that observation. And we're going to use what we were talking about the wedge product before. We're going to write B wedge A as the magnitude of B times the magnitude of A times the sine of the angle in between them, which in this case, what's the angle in between B and A? That was gamma. So sine of gamma times E1, E2, but I'm going to write I for short. And this has to be equal to A wedge C. So that's going to be the magnitude of A times the magnitude of C times the sine of the angle in between them, which was beta, also times I. Now, if the two bivectors are going to be equal, their magnitudes have to be equal. So that means that the magnitude of B times magnitude of A times sine gamma is the same as magnitude of A times magnitude of C times sine beta. And instead of writing length, the absolute value bars of big B, I'm going to write lowercase b to represent the length of B, of the vector B. And I'm going to write the lowercase a for its length times the sine of gamma is equal to little a, little c, sine of beta. So just equating the magnitudes there. And I have a look. I cancel out the a's from both sides. So I have that b sine gamma is equal to c sine beta. And I do a little bit of rearranging. I divide both sides by b, bring the b down there. Divide both sides by c. That's going to bring the c down there. And I can rewrite this in the common form for the law of sines. Sine beta over b is the same as sine gamma over c. And you can cook up a similar argument that we were doing before to show that this and this are also equal to, as you would expect, sine of alpha divided by little a. So that's another take on the law of sines using the wedge product concept. And you can view this law of sines as being a consequence of the demand that the two parallelograms that we're talking about, that formed from B wedge A and that formed from A wedge C, having to have the same area. Let's now tackle the law of cosines. So I'm going to return to the triangle that I constructed before. I have the vector B added to another vector C to form the vector A. So once again, I have A is equal to the vector sum of B and C. Now what I'm going to do is I'm going to solve for C. So I can write C as A minus B. And now I'm going to pull a little trick out of the hat. What I'm going to do is I'm going to square both sides of the equation. So on the left-hand side, I have simply C squared. And on the right, I have A minus B all squared. But that can be rewritten as A minus B times A minus B. And now what I'm going to do is I'm going to distribute this right-hand side. So first I have A times A, or A squared. That's the first term. Next I'm going to multiply minus B by minus B to get B squared. Next I'm going to multiply A times minus B to give me minus AB. And lastly I have minus B times A. So I have minus BA. And I remind you that the geometric product doesn't commute, so that's why I had to be careful with the A, B, and BA. I can't just swap them as I'd like. And that's still equal to C squared. Now let's observe something here. Let me rewrite the right-hand side just to make it a little bit clearer. Let me pull a minus sign out of these two terms. So I have minus the sum AB plus BA. Now hopefully you recognize this thing, AB plus BA. That looks pretty similar to the dot product. So remember the dot product, AB plus BA. But now 1/2 that was actually equal to A dot B, which means the thing we're looking at here is actually 2 times A dot B. So I'm going to make that substitution. So I have that this is equal to A squared plus B squared minus 2 times A dot B. And that's still equal to C squared. So that's what we have so far. And to complete the derivation, we're going to recall a few facts about the geometric product. Notice that we have a bunch of vectors being squared. And remember that when you square a vector, that's equal to the squared length of the vector. So I have C squared here. And I'm going to designate the length of that vector by lowercase c squared. And I have big A squared. I'm going to designate the length of A as little a squared plus little b squared. And then I have 2 times the dot product between A and B. But what's the dot product equal to? That's going to be little b times cosine of the angle between A and B. The angle between A and B was gamma right there. So this is equal to, this last term is equal to minus 2AB cosine gamma. There's a very important special case here, which is when gamma goes to 90 degrees. So that triangle is going to look something like this. There's A. There's B. And C right there. A and B have an angle of 90 degrees. So what happens there? The dot product between A and B goes to 0, which means I'm left with the Pythagorean theorem, which is c squared is equal to a squared plus b squared. So you can see, well, you might already know this, that the law of cosines is a generalization of the Pythagorean theorem, and the Pythagorean theorem is actually a special case of the law of cosines. There are 2 other formulas you can derive for alpha and beta instead of gamma, just by cycling through the letters A, B, and C, and the angles alpha, beta, gamma to get the other 2 formulas. So I encourage you to verify that. And I think that'll do it for this this blast from the past of high school trigonometry from the point of view of geometric algebra. So hopefully you enjoyed the video. If you like my content, feel free to subscribe, leave some comments on the video, and I thank you for watching.